So this is going to be a not so brief aside on vector math. You'll see a few, these slides are versions of these slides kind of repeated in various lectures to remind you. But this lecture is going to be here as kind of a standoff that you can review independently and a little bit shorter than maybe some of the other lectures, so that you can just take a look at it and review vectors, because vectors are going to come up a lot all over the place. We're going to use them kind of constantly. And so it's good to familiarize yourself to at least the level that we're discussing here. You don't need to be an expert, you don't need to know all of the algebra involved, but you should feel pretty comfortable, especially with the graphical nature of the way the vectors work. So these are some basic operations we do with vectors. The thing to remember about a vector is that it really represents a direction. So it doesn't necessarily matter where it's located in space. It can be anywhere. We can sort of put the tail end of this vector somewhere, and what we're saying is wherever we start this vector, we're going to go in that direction. Now if you decide to put this vector at the origin, which is the 0, 0 mark, then you're actually saying I've got a position in space. So if this origin is my world position, which is 0, 0, 0, so if you set your vector at the origin, then you can say that your vector is kind of a specialized form, that it's now a position, because now x and y represent the position in space that vector is pointing at. But really, for the most part, vectors are considered a direction, and sometimes they have a length to them. The length is always something, right? It's always some length along here, depending on how far x is. So x describes this direction and y describes this direction. And how far that is how far the vector goes. And so we can, think of it in speeds or velocities, directions going that way, or we could think of it as rays coming off of something that we might intersect with. There's a lot of uses for them, and we'll see many of those uses. But these are some of the basic math operations that we do with them. So we might want to add two vectors together in order to understand how we might say combine a path, right? So if I'm going to go this direction for this long and then this direction for this long, where do I wind up? Well, if I start here, let's just say I start at whatever position this is in the world, and I go this direction, then I wind up here, right? And so let's say this is the origin, which is fine. That's sort of the 0 origin. So I end up at x1, y1, because this is 0. Then I add x2, y2, and so I end up at the sum of them over here. But I can think of that as a new direction that is this length and goes in this new sort of direction. So I can actually put the fact that I want to do x1, y1 and x2, y2 as a combination path anywhere in the world. It doesn't have to have started at the origin. It can start anywhere because it's a direction. And when I add them, I consider putting the tail of the second vector to the head of this vector, and I walk first along this vector, and then I walk the tail of this vector. So we see that here. Here's the first vector, and then I walk along the tail of the second vector. And I kind of draw my new vector as the tail where I started from and where I ended up to, the head where I ended up to. And that's what it looks like graphically. And then in the math, I pretty much just do this. I add the x's together and the y's together. Okay, so for the most part with vector math, or with vectors in general, we kind of operate independently on each dimension. So we do the addition in each dimension. And if we had a z, we'd have a z1 plus z2 over here. But that's the nice thing about vectors. You can sort of think of it with two space, like a 2D space like this, but really it can represent 3D space because all of the dimensions operate independently. For the most part. You expand it pretty easily to the third dimension, or even a fourth and fifth dimension, but we're not going to go there. Okay, so similarly, if I wanted to subtract the vectors, much as we do, so when you think about arithmetic, you can kind of think of never having to actually do subtraction if you know how to take the negative, right? So if you take the negative of a number, then you can just add the negative of that number to another number, and you're not really doing subtraction anymore, you're just adding a negative. Well, it doesn't make sense, because when you add a negative, you kind of have to do the subtraction, and you need to understand how number lines work. But it makes a lot of sense with vectors. So when we think about vectors, when we think about subtraction, we can say we're going to add the vector, but we're going to add the negative of this vector. And the negative of any vector is just the vector flipped. So we really just take the arrow and put it on the other side, and that's now our new vector. And that's really the only difference that we have to do to flip a vector. So then, if we do the addition in terms of the graphical version, we flip the vector and then we add the flipped vector here. So that's what we see over here. So we take our first direction here, which is this one here, and then we flip our vector and we go this direction, and we wind up with a new direction that is completely different than this first one, right? As we would expect, because we're subtracting them rather than adding them. But it really looks like addition again, right? Because we put them tip to tail, as we did before. So tail, tip, tip, tail, and then another tip here. And then we draw our new vector, much like we did with the addition, but first we had to remember to flip this vector. Right? But the math looks like this. So we say x1 minus x2, and y1 minus y2. And then again, we would say z1 minus z2, and it would move in the third dimension as well. So then finally, we do sometimes want to do things with single numbers. So what we think of when we multiply a single number by a vector, scaling a vector like this, multiplying it by a scalar by a vector is extremely common. We're going to do this a lot. So we're going to have things like a direction that we want to move something, say back and forth, and then we have a speed that we move it with. Right? So we have this is just going to represent our direction. It's not going to have any speed associated with it, and then we're going to multiply our speed by that vector. And when I say it's a direction and it doesn't have any speed associated with it, what I really mean is it's a length 1 or a unit vector. And we'll see that in a minute. And so a vector which has unit length means that it really doesn't go kind of anywhere. And then if we multiply it by s, we actually get a new vector which is of length s in any direction, right? So this arrow, of course, is pointing up, but we could also imagine this arrow pointing in any direction, much like these others are. And then as long as it's unit length, multiplying by s scales that vector by s. Now it also scales it the other way. If it's a length 2, then the length becomes 2s for that vector, if the vector was of length 2 before. But that's of course why we kind of like it to be of unit length, because then we know the length after we multiply it by this is now of length s. And so again, that's scaling the vector. So this is like, we do have a direction and now we want to move at a certain speed, or we have a direction and we want to move a certain distance along that direction. That's the kind of thing that we're doing here. And so a scalar, when it's multiplied in this way, simply multiplies each dimension itself, right? So we see s times x and s times y here, right? So x2, y2, sx2, sy2, and we see that the vector grew longer by s. There is a sort of multiplication that we do, and you can do a straight multiplication, which is known as kind of scaling the two vectors by scaling a vector by a vector, but that is much less common to do. But projections are very common, so we're going to see this in a lot of different contexts. The dot product, and the dot product is this idea that we multiply, we sort of turn these vectors into a single value. Okay. So what we're doing, and I'll start with the math, and then we'll kind of go back and understand what's happening, is we multiply the x1 by the x2, and we multiply the y's together with the y1 and the y2, and then we add those results. Okay, so we get x1 times x2 plus y1 times y2. And so the idea here is, or sort of the core idea, is that in some sense the dot product gives us a projection of one vector onto the other. And it doesn't really matter which order we do this in. And if you look at the math, you understand how you can do, I think it's the associative property, the commutative property, and I tend to forget. But because of those properties, we can swap these two, and we still get the same answer. So we do think of projecting one vector on the other, but it depends on what we're thinking about when we do it. But the answer ends up being the same either way. So the projection of this vector onto this vertical vector here, we can think of as kind of just taking the shadow of it, right? So if we were to cast a light beam this direction, it would take up this much length in this direction, right? And so that's what this projection, the projection of this vector onto this one is. You could also think of that as taking up this vector takes up this much length on this vector as well, but it's a little weird to look at because this vector is sort of in a skewed direction, whereas this one's just straight up and down. It's a little easier to look at and understand what's happening. But we'll kind of go back and look at that in a little more detail in a second. But let's take a look at this in practice. So let's use some just easy vectors and understand kind of what's happening. And so we see, here's a vector which doesn't go in the x direction at all. It's straight up and down. Here's a vector which is straight up and down. And if we do the dot product together, we get a length of 1, okay? Or we get a dot product value of 1, which means that we sort of just take in the projection and we just get, this vector goes, because they're exactly the same distance, this vector goes along this direction one distance, right, in sort of the vertical way. Whereas over here, if we have 1, 0, so it's a 1 along the x, but it's not going any vertical along the y, now we get a 0 projection, right? So we're multiplying the 1 time the x's together, the 1 times the 0, and then the 0 times the 1 over here, We get a result of 0, and that, we see the same kind of thing, right? If we imagine a light shining here, we see that this really takes up no distance along here at all. There's no vertical direction, right? And so we can almost think of this in this case as kind of breaking out the direction. We're sort of figuring out, well, how much vertical direction do you have? Or this one has all of its direction in the vertical, and this one has none of its direction in the vertical, right? And so if we take a vector like this, which is diagonal, and we want to figure out just how much of the vertical direction it has, we can still do the dot product, and we say, okay, well, how much of the vertical direction do you have? We take the dot product, we figure out, oh, okay, you've got 1 in your vertical. Now you can almost imagine too, then, what if I take a vector going this way and it's a 1, 0, we take this vector, then we know that we also get a 1 in the horizontal direction, but now we're getting the other direction. Okay? And now we're getting to somewhere interesting, and we'll see how that takes us further. So then the length of a vector comes back all the way back to Pythagorean's theorem, and hopefully this is not new to you and you've seen this kind of thing before, but it's the whole length of a triangle, right? So if we think of our vector here as the hypotenuse of a triangle, or C, and this is our vector, then this is kind of our x coordinate and this is our y coordinate. And we know from Pythagorean's theorem that c squared equals a squared plus b squared. And you might have heard it the other way, right? A squared plus b squared equals c squared. And hopefully that feels very comfortable to you to hear as a kind of a rhythm, right? Really, the key point is if we take the square root of both sides, which you always do operations together on either side of the equal sign. We say take the square root of c and c squared and take the square root of a plus b squared. And what we get is that the length here is the square root of the square of these two guys. Right? So if we take a squared, whichever length this is, and square it, take whatever length this is and square it, and we take the square root of that, then we get the length of our hypotenuse, the length of this part of the triangle right here. So, as we already kind of looking at, if our vector is that hypotenuse, then this is our x coordinate, and this is our y coordinate, right? How much vertical it has, how much horizontal it has. And when we take the dot product of a vector with itself, we essentially get this a squared plus b squared, except we're getting x squared plus y squared, right? So rather than a and b, we're using x and y. So we get x squared plus y squared. So if we take the square root of the dot product, we get the length of our vector. And so this becomes useful because now we can test whether or not our vector is actually length 1, or if our vector is length 2. And you might even look and say, well, what if I did have a vector of length 1 in there, and I had the s in there, and I have like s squared, and then I've got this s squared pulled out. Well, somehow I should, if I do all the algebra, and you can work this out for yourself, I should get s back out, right? Or s times the remaining length of the vector. I should actually get an s out of that, and you do if you do the algebra. And so I challenge you to do that as an exercise for yourself. But the point here is that we can figure out the length. So we can use the dot product here in multiple ways. One, we can do the projection, and two, we can do the length, which means that we can do this other process called normalizing a vector. So normalizing a vector means that we take its length and we divide the vector, we scale the vector. We're actually coming back and we're doing this scaling operation, all the way back here. We do this scaling operation, but we do it with 1 over the length in order to scale the vector to be length 1. Okay, so this is if we have a vector which is not unit length and we want to make it be unit length or make it be normalized, we do this procedure. So here's an example. So we're going to take the vector 4, 6, so it's going 4 in the horizontal, so 4 on its x-axis, and 6 upwards, and you'll have to trust me that that is definitely what this arrow is doing. It's not at all skewed in any way or drawn incorrectly. I'm kidding, of course, it's probably drawn somewhat incorrectly, so don't measure that. And we're going to say, we're going to dot product these two together, so we're going to dot product 4 and 6 and 4 and 6, and we're going to take the square root, and what we get is 7.21, and actually it's 0.21 and 22 something, I don't remember now, but if you plug it into your calculator, you'll get a few more digits over here, and if we saved them all, then we'd probably get a better answer, but we're going to get a pretty close answer anyway. And so what we want to do when we normalize is we essentially divide. We take this scalar, right? Remember, this is now a single value, a scalar value, not a vector value anymore. Represents just a straight number. And we take 1 over that length, right? So this is the length process up here. So we take 7.21 here, length of our vector, and multiply it, or really divide our vector by the length. But we'll say we're multiplying by 1 over the length, which is the same as dividing by the length. And what we end up with is what we expect is to get a vector which is length 1, so or unit length. Okay, so and we refer to that as being a normalized vector or a normal vector. Now we also refer to a normal vector as something else, especially in graphics, and we'll worry about that later. So we'll use the term normalized to refer to a vector, or a unit length vector to refer to one that is unit specifically. So if we take 1 over 7.21, what we're going to do essentially is take 4 and divide that by 7.21, and 6 and divide that by 7.21. And remember, this procedure here, we're scaling by this scalar here, so s times x and s times y. And we divide, so we multiply by 1 over, or divide by 7.21, and hopefully that feels comfortable to you to do that kind of arithmetic. And we get a result which, what we might expect, of course, is that if we want our length to be less than 1, these guys better probably be both less than or equal to 1. And we get that, so we're always going to see a normalized vector is going to have these guys be less than or equal to 1, these two values. Now it might be that one of them is 1 and one of them is 0, which of course we already saw. That's a very simple one. But, you know, if we're looking at off directions, then we're going to start to like lower, and we think of almost a circle, right? A circle of radius 1, and so it starts to lose its distance here, but it gains more distance over here, and so on. What we end up with is this vector, and if you do this same procedure up here with this new vector, what you should get is something close to 0.999 here. Right? In fact, you get 0.999 like 1 something, I think, over here. And of course, that's because we rounded off a little too early over here, and if we kept all the digits of accuracy, we'd get much closer to 1. And so, of course, with some computer math, we always get these kinds of errors, but as long as we're pretty close, we can treat this vector as 1. Okay. So now this is the way we get to a normalized vector. So when we talk about normalized vectors, if you imagine any vector at all, then you can always imagine it normalized by simply figuring out its length using the dot product and then dividing by the length. Okay. And remember, you can't. This lecture will be available throughout the semester, at least once it's first become available. And you should think to refer back to this often to review and remember, especially if this is new to you and you're not sure what these things mean and how to use them. Now, the first time I saw this and understood it, I found it a little mind-blowing, and some of you have probably seen this, and some of you might not have seen this. It might be a bit to walk through, but I encourage you again as you go through the semester to kind of look back at these and understand, or try to understand what's happening and ask questions and so on. But let's take a look at doing multiple projections of the same vector. So here we're going to reuse this vector x1, y1 2 times, and we're going to take a red direction and a blue direction. And what we're going to say is that the red direction is of unit length, and now we know how to make sure that the red direction is unit length, it's normalized, and the blue direction is of unit length and it's normalized. And we do our projection as before, and so what we understand is now that this is going to give us the length of the red vector along the black, or the length of the black along the red, or in the direction of the red, right? So how much of that black is going along this direction, and it's the same value, and we treat that as the value a1. Okay? And then we do the same thing for the blue here. We say how much of the blue is going along the black direction, or really how much of the black direction is along this blue direction here. Okay, so how much of black goes along here, and it's only this much this way. Right? Same thing, same value, and we store that as b1. And then what we say, or what we've set up in this particular case, is that red and blue are orthogonal to each other. They are perpendicular to each other. So that means that blue and red make a 90-degree angle, or they're at a right angle to each other. So they kind of go in two sort of incongruous directions. And really, if we were to take the projection of blue and red together, we would get 0, because they don't overlap at all. Right? The amount of space that blue covers in the red is 0. If we think of just the straight shadow this way, if we were to project the shadow that blue makes on red is 0, or the shadow that red makes on blue is 0. There's no shadow there at all. And so, even better, we can now think of them as being sort of new directions to represent this black vector. So we can think of it as their 90-degree angle. Our red becomes our horizontal, and our blue becomes our vertical, right? So that's a horizontal. We normally think of the horizontal as being perpendicular to the vertical. So we simply just treat them that way, right? So by virtue of just having two perpendicular axes, we can sort of just pretend now that we know what this black vector is in a new space, in a new orientation, right? And so this is actually how we figure out new orientations for vectors. We actually haven't changed the black vector at all. We're just looking at it from a new perspective, from a new direction, so to speak. And I drew these blue and red arrows intentionally because we've already seen the blue and red arrows. And when we think of, and of course we can imagine a green arrow representing our z and having our third dimension that way, right? By simply doing a dot product with the third vector and getting a c value or a z component out of it. So we refer to this as a space because now we can think of this vector being projected into this space. So rather than simply projecting vectors, if we do a dot product with three vectors, or two or three vectors, we're projecting into that two or three-dimensional space, a new space entirely. Right now, these vectors initially are essentially defined in sort of the world origin space. We imagine this direction as being in the world space. They're sort of globally defined. And this vector is defined in the world space. But by doing this dot product, we project this vector into this space, and we really treat it as new vector A and B. And you know, my drawings are a little bad here. I don't think my black arrow is quite right. But if you do you should maybe plug in some numbers yourself and convince yourself that this kind of thing works, especially if you want to understand it very well. It's good to work with real numbers, but I'm not going to show you real numbers for this example. So this works for the reverse. So I have said, or declared, that we did not change the x vector at all, and that's true. So we can get our x vector back. A and B still represents that x vector, but it represents it in this new space. But in this case, if we're in this space, we should already kind of be comfortable with the idea that if I have an A and B, and note that the scales here are kind of completely wrong. We didn't really rescale this black vector at all. But if I have an A and a B vector, then if I walk along the horizontal, if I have an x and a y, if I walk along the horizontal of the x, then I add in the horizontal of the vertical value of the b, I get to my vector, right? That's kind of how we see vectors anyway. That's how we knew we could do this whole triangle inequality in the first place, right? We walk along x, and then we walk along y, and we get to our vector. Well, we can still do that. We just do it without the vectors necessarily being in the sort of normal orientation that we expect for axes to be in, right? Now we're going to say, well, I'm going to walk a distance along this red vector, and then when I get there, I'm going to stop, and I'm going to turn in the direction of the b vector, and I'm going to add that in. I'm going to walk along the b vector, or the blue vector, in the direction this way, right? And so really it's the same thing. So I scale the x vector, which again is unit length. So this is the important part. It's unit length, and I'm going to walk this way by a distance, because if I multiply anything by 1, I get it back. So I know that the length, if I multiply this by a, is going to be length a. So I'm going to walk a this direction, and then I multiply this one by b1, sorry, a1 and b1, and I'm going to walk along this direction, and what I get is this. So I walk along a1 in this direction, I walk along b1 in this direction, and I get back to my original black vector. Okay? So I want you to understand this graphically, because this is very useful to know as we talk about spaces, as we talk about projecting in and out of spaces, and understanding our object orientation and our camera orientation, and when we're doing collisions, and when we're trying to cast rays, and all these kinds of things that we're doing this sort of stuff with. This helps us to understand all of that, at least understand it at the graphical level. Now, if you are very brave, I highly recommend you try to work through the algebra, actually figure out how this dot product looks in terms of x1s and xa's, and see if by going through this whole process, reversing this whole process, you can get back to x1 and a1, or x1 and y1 with your coordinate vectors. It's non-trivial, but it's an interesting process to work through, and you do need to know the fact that the dot product of two vectors which are perpendicular to each other becomes 0. Okay, so and one last time, I encourage you to refer back to this lecture, to refer back to the other resources regarding vector math, and at least understand how this all works graphically, and a little bit how it works mathematically in terms of the algebra. Of course, Unreal is going to actually take care of a lot of the basic arithmetic, right? So we can just use the operation I want to scale a vector by a float, and we've already used that a couple times at this point. And Unreal does that for us, and so that's great. But it's worth understanding what we're actually doing, at least in terms of what we're doing with the vectors, what it means to scale a vector, what it means to have a unit length vector, or to even especially to normalize a vector and turn it into a unit length vector. So I encourage you to come back and review this and remember, and especially as you start using more and more vectors, to familiarize yourself with this, so that a lot of these systems start to feel really comfortable, and you feel that much more comfortable using them and understanding what's happening beneath the hood, so to speak.